All right, so let's keep going and let's do the drawing of the joints. So some stipulations here. You must use your own matrix stack, which we have the code completed for, to perform the transformations. We have just went over how we can work with this matrix stack to move spheres around. So hopefully you have an understanding now of what's going on and how the stack is helping us account for floating point error as we undo transformations that we put on the stack, and we're going back to where we were earlier. This is important for traversing a hierarchical model, a hierarchy. Anyways, so that is important, and we understand how it's working and how we can tell OpenGL to use it. Yeah, so the other thing it says here is you need to recursively draw the child joints. So if you have heard of recursion but it's confusing to you, or if you already know what recursion is, then great. If you've never heard of recursion, let's talk about that for just 1 second. So let me jump over to Excel again, because that seemed to be helpful earlier. So if perhaps in your math class you've seen f of x is equal to, and then if I said my f of x was equal to 3 plus f of x, this is kind of just silly, but let's see if we can find f of 3. I don't know, it doesn't really matter. So f of 3 is going to be equal to, well, that's going to be 3 plus f of 3. Well, that's going to be equal to 3 plus 3, let's do parentheses. So I'm replacing f of 3 with what f of 3 is, like that, and then, okay, well, we need to replace out this f of 3, and you can see we're sort of just drilling down, deep into what is known as recursion. So you keep drilling down, and the function is defined by itself, and this will go forever. But in computer programming, you can actually just set a little flag and say, like, let's say we're doing a little counting variable, and it's every time you do this, we're tracking another variable that's counting up how many layers down we go. And let's say when we get to 6, we're going to stop. So when we get to 6, we're going to stop. And instead of saying f of 3 again for f of 3, it's going to be more like of a piecewise function. So it'll be equal to 1 when we're at iteration 6. So then, our things start to come back up from that recursion. I'm not even going to attempt to write this, but instead of doing another parentheses and then 3 plus f of 3, it'll just do parentheses 1, and then you do 1 plus 3 plus 3 plus 3 plus 3, and you come all the way back out to the top and you find your solution for recursion. So that is a really quick crash course on recursion. The idea is you're calling a function inside of your function over and over again. But we can also program a little flag or a little signal that says, hey, stop, we're at the bottom, let's start going back up now. And that is a quick idea of what recursion is. And we're going to do that recursively for the children joints. So the idea is we are going to go to a child and then go to all its children and then go to each of those children's children, and we're going to drill down until there are no children, and then we'll come back up. Yeah. So with that said, we are going to be working. Oh, what did it say? We're going to be working in the drawJoints function, and we're using the solid sphere. And we've already kind of played around with that right here. So, we've already talked about what happens as you push and pop and use the GL load matrix code. And how that controls where we're going to be drawing. I do encourage you to spend some time experimenting, but let's continue on now that you have some intuition for how that works. All right, so the cool thing about this matrix stack thing is really, and the VecMath library and all this stuff, really the cool thing is we're using hardcore linear algebra. Like, we're using linear algebra that you learned in a linear algebra class, but instead of you doing the matrix multiplications by hand, everything has been abstracted away from you. So like we can just work with these tools, and we don't have to actually worry about computing a matrix multiplication. The computer's going to be doing that for us. And I think that's really exciting. And I've heard in a couple of lectures, like, that is really what linear algebra is meant for. Like, when they teach linear algebra, you have to do a matrix multiplication on a test. But the beauty of linear algebra is you're really not meant to worry about how the matrix multiplication gets done. Instead, you want to gain an understanding of working with those tools in that space, and you don't have to really think about like doing all the hard work. You leave all the hard work for the computer to automate that for you, and you get to just like, you know, work with the fun parts of linear algebra and get an understanding from there. So that's what we're going to start to dig into with this project, and I think that is pretty cool. So let's start digging into writing some code. So before we get into recursion for this, let's kind of look at how do I want to do this? Let's get okay, hold on. Let me bring this back. All right, so we're pushing on a translation, and then we're drawing or painting a sphere right on that translation. So we need to get our transform for the joint. All right, so let me just get out a matrix for F. We'll call it T for transform, and let's just start with the root joint. All right, and we'll get its transform. Ooh, it did not autocomplete that. Sorry, we need the root joint. Root. There it is, root joint, and let's get its transform. So I'm using the arrow operator to access its properties or its members, and we'll get the transform. Great, and transform is of type matrix 4F. So we're saying a matrix 4F is equal to matrix 4F, which makes sense. Okay, and then, you know, instead of pushing this translation, that was an example, let's push on T onto the stack. And let's see what this gets us. All right, so what we've just drawn is we've drawn a sphere at the position of our model. And I've already seen the solution, so I mean from here, this is our root. And we're going to start drawing some arms from there, and then some hands, and then, you know, a pelvis, and then some knees, and then some feet, and some toes, and stuff like that. It's all going to be drawn from here. Cool. All right. Now, we don't actually need a sphere at the root joint. Instead, we want to draw spheres for everything else. So let's get the root joint's child. So we're not going to get child 0 because that will be the root joint. And that is, again, something particular to my code. I put the root joint as a child to itself. So the very first thing that got parsed was our root joint, and the very first child that was added to our root joint was the root joint. So that's why I'm skipping 0 and I'm going to 1. So I'm going to get the first child, and I'm going to get the first child's transform. So, oops, sorry. Children transform. There you go. All right. And let's see what this looks like. Yeah, let's see what this looks like. So I'll hit play. So now instead of doing the root joint, we're just going to the first child of the root joint. And this is what we get. So this is a transform from the root joint's position. So basically what happened was we lost that position, and really this guy is supposed to be a child of the root joint's transform, And it's going to be a transform from the position of the root joint. So what we instead have is a transform from the origin. And that is because our matrix stack does not have the transform of the root joint pushed onto it. So again, it's that problem of going to here in our example from a little bit ago, and then going up and then back over here to get this guy. We need these guys to be drawn in a hierarchy in a relationship to each other. So what I'm trying to say is that we don't want to push on the child without having its parents, without having the parent transform pushed on first. Okay? So now if I come in here and I copy and I come underneath and I paste, and then I remove the declaration of variable t. And then for the first guy, for the first push, I'm going to push on the transform of the root joint. Like that. And then the second push will be the transform of the first child of the root joint. So we're going to do transform of the root and then the transform of a child. And then, so it'll be from the position of the root. All right, let's see what that looks like. Okay, so this is looking better. And if we look at our data here, this is our root joint, and then this is the first child of our root joint. He's saying that his parent is position 0. And we're seeing that the transform is actually 0, 0, 0. So we're not even moving from the root joint. All right. Okay. So we're going to keep that sphere. And then what we're going to do is let's pop off. So let's pop off that transform of the child. So we're popping off child 1 transform, and then let's push on, and we're going to keep the sphere drawn, and then let's push child number 2. And child number 2 is actually going to be another 0, 0, 0 transform. So maybe that's not a good idea. Let's not do that. We're going to get the second guy that's saying its parent is number 0 is also a 0, 0, 0. So let's not do that. I'm changing my mind on the fly here. Instead, let's keep this on, and let's get the child of the child. And let's see what we get. So this time I'll do child number 0. So the very first child in that list of children. Let's get its transform. Let's push it on. And let's load that matrix stack top, and let's draw a sphere right there. Let's see what we get. Give that a minute to load. All right, this is looking kind of cool. So now what I want to do is, instead of getting the first child of this child, let's get the second child and see what that gives us. So first we're going to the root transform position, and then we're getting the first child of the root transform, and then we're getting the first child of that child, getting its transform, putting a sphere down. So now let's pop off that first child. So matrix stack dot pop. And then we'll copy this code again. So we're popping off this first child of the root joint child. We're popping that off. And then now we're going to get the second child transform and draw a sphere. What happened? Exception thrown. Oh, so I believe what happened was the first child of the root joint does not have another child. So instead, let's do this. We'll keep that guy, and then we will get its child and see what we get. So sort of what I'm doing right now is I'm giving you an idea of what your recursion function has to do. Okay, so here's what we get. We're getting the first child of the first child of the first child of the root joint. And we're sort of getting a spine getting drawn here. And that is pretty cool. So let me stop this. And what I'm doing is I'm setting you up, in case if you haven't attempted it yet, I'm setting you up to attempt to write this recursive function. Okay, so I'm going to come up here and I am going to go right above the drawJoints, and I'm going to define the recursive function that we're going to call inside our drawJoints function. So skeletal model, : I'm going to call mine Recurjoints joint, and it's going to accept a joint address as an argument. I'm going to call it node. Just going to kind of give you a an idea here, and then if you're following along exactly with what I'm doing, here is the code that you need to call the recursive function. So this will be a GL load. GL load. What am I missing? Matrix F. There it is. And then M matrix stack dot top close parentheses semicolon. Let's get a for loop going. For should be able to auto complete more of that. For I, there it is. So for I is equal to 1. I is less than, so for the root joint, for its children vector, for the size of its children vector, we're going to iterate through all of the children, and we are going to call our recurjoint function on that root joint's current child that we're looking at in this loop as we're iterating through. We're skipping the first one because the first child of the root joint is the root joint, so that's why I put 1 here. If you did not put the root joint as a child to itself, put a 0, and then this should still work. And it says that is undefined, but that is okay. That is because we did not put an instantiation in yet. I will show how to do that in a second. And then when we're all done, we want to pop off, and then we're going to load the top, because we don't know who's going to use this stack next. Just for some housekeeping. Okay, so if I come up here, this is all red, but if I click on this, I got a little wrench. I can't remember if this is built into Visual Studio Code or if this is because I have the ReSharper JetBrains tool installed. But if I click on the little wrench, it says create a declaration. I'll go ahead and click on that. And then what that just did is it inside of my skeletal model.h, it just typed this code right here. It put in an entry in the public member functions of this class. There is now a recurjoint declaration. So I will go ahead and save this and go ahead and save this. And I should have kept the code that I wrote on the screen, but I recommend rewinding and kind of looking at what was happening as I drilled down into the children, and what, each time you go to a child, what you need to do next in order to get the computer to automatically crawl down this tree of parents and children, and draw a sphere, and then go to the next child, do all the children, draw spheres, 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 and then at each child you'll go to all the children, draw spheres, 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 and then depth first traversing of the tree. I believe that's what I did in my code, depth first. So that means you drill down as deep as you can, draw a sphere, come up, go as deep as you can, draw a sphere, come up, draw a sphere, come up, draw a sphere, come up, and then do all the children, draw sphere, draw sphere. So you go all the way to the bottom, and then you come up, and then you go all the way to the bottom type of thing. So yeah. So let me pause the video here, give it a try, and then we'll come back and I'll actually fill out what I did for this recursive function.